Today we're going to get into our next and really last gas law. So up to this point, we have looked at Charles, Boyle's, Gay-Lussac's, and the combined gas law. And they all have to deal with a change of some sort, a change in temperature, a change in pressure, a change in volume. They all are a before and after comparison. What we're going to work on today is not a before and after comparison. It's a snapshot of a gas at one time, right? And we're going to be able to determine how many moles are present or how many liters it takes up or whatever. But that's the difference in what we're doing today versus what we've done so far, right? So far, we've looked at gases that are changing. But right now, we're looking at just a snapshot of a gas at a single time. So to get kind of an introduction with this, we're going to look at something called Avogadro's principle. And Avogadro did all sorts of things for chemistry, right? His number that relates to the number of atoms or molecules, right? 6.022 times 10 to the 23rd tells us how many molecules are present in 1 mole of any substance. But he did the same relationship for gases. All right, through a bunch of studies, he found that 10 liters of hydrogen gas and 10 liters of oxygen gas at STP both contain the same number of particles. So it has nothing to do with their mass. It just has to do with their quantity. And so his math and all of his experiments led him to this conclusion, is that a mole of any gas particle at STP has a volume of 22.4 liters. 22.4 liters. So that's something you can highlight. You can put it on your equation sheet if you really want to, but a mole of any gas at STP is going to have a volume of 22.4 liters. The reason that's important for us as we start looking forward throughout the chapter is that we're going to be able to use that knowledge as a conversion factor when we talk about stoichiometry in gas particles, right? We'll be able to figure out, if I start with a mixture of 10 liters of one gas and 10 liters of another, how much gas can I produce, right? We're going to start doing stoichiometry with gases, and this can help us be a conversion factor for that at STP.
So on the test, will we have to
All right, so we're going to move into what's called the ideal gas law. The ideal gas law is where we look at temperature, pressure, moles of our substance, and volume, and how they correlate for an ideal gas. All right, this is for when particles are not at STP, right? If a particle is at STP, we already know its pressure, we know its temperature, we know its volume as long as there's 1 mole of it. Okay, and if there's not 1 mole of it, we could calculate it based on that 22.4 liters conversion factor. So at STP, it gives us really, really simple calculations. But when things are not at STP, then we're going to be able to figure out what are the conditions for this gas. So here is the equation for the ideal gas law. PV equals nRT. Okay, 4 of those probably look familiar to you, but 1 probably doesn't. All right, so P is for pressure, V is volume, N, we talked about the other day, is the number of moles of our substance. R is the one that's new for us. It's the universal gas constant. So it is truly a constant. It's the same every single time. So the R value, I'll give you that here in just a second. And then our T value is temperature. Okay, your R value is right on there on your slides, I think. But the R value that we are concerned with is this top one. This is the one that we're going to prefer to use. Okay, we're going to want to use this top R value. 0.0821. 0.0821. Okay, and the reason we would prefer to use that R value is because the units are what we like to use, right? The units for volume is liters. The unit for pressure is atmospheres, moles, and then the temperature unit is Kelvin. If you look carefully at the other option for the R value, the unit for volume is decimeters cubed. We don't ever use that, okay? And then kilopascals, which we could, but we don't use. Okay, so the reality is that in order for our ideal gas law to work, for us to be able to use this constant, we have to have our pressure unit in atmospheres, volume in liters, moles, and then we have to have our temperature in Kelvin. So that's why I've kind of prompted you with converting to those things before, so that in order to use our ideal gas law, we've got to have things in that unit. Okay? R value is something that you're always going to know. It's not going to be specifically written out for you in problems, right? You have to be able to remember what the R value is or have it written down for you to be able to plug that in. Okay? Questions with that? Otherwise, it's really simple algebra, right? Because it's pressure times volume equals moles times R times T. Okay? So I want to show you how this, the units for R came about, right? We're going to put in all the things that we know about 1 mole of a gas at STP. Okay? If I rearrange my equation to solve for R, okay, if I rearrange my original equation to solve for R, PV equals nRT. And if I rearrange this to solve for R, I take NT on both sides, and that gives me R equals PV over NT. And so I plugged in here all the information that we know about a gas at STP. If we have 1 atmosphere, we have 22.4 liters, 1 mole, 273. And if you do that math, voila, it comes out to be 0.0821. Okay? So that relationship is going to be there all the time. And so that constant allows us to be able to look at the direct correlations and the different situations. Okay? We use the ideal gas law when we're only given one set of our conditions. So we're not given a before and an after. Right? You said the ideal gas law is just a snapshot of one time. So we're not seeing a change. If we have a change in volume or a change in pressure or whatever, we might need to use the combined gas law, okay? But if we don't have that, if we just have one set of conditions, we'll use this. R is a constant. We know what it is and we won't have to solve for it. You'll be given what you need to solve for one missing variable, okay? So the ideal gas law is really just plug it in and calculate it, right? It's pretty simple. Plug it in and calculate it. So this says calculate the pressure of in atmospheres of 0.413 moles of helium at 16 degrees. That occupies 323.25 liters, excuse me. So I'm going to make my list, okay? Calculate the pressure. That's going to be my question mark. 0.413 moles, so that's N. Okay, my temperature, can I keep my temperature in Celsius? No, I cannot. So if you don't have your calculator, let's go ahead and grab that calculator out so we can get our temperature value calculated. 16 plus 273 gives me 289. And my volume's 3.25 liters. All right, so what's the one thing missing from my list here? I don't know pressure, but I'm not writing down R for my list. You're both right. Okay, I'm trying to calculate pressure, but I don't need to bother writing R in my list, right? I know what it is, okay? So I'm just going to leave that off my list, and I'm going to start putting them in my equation now, okay? So P times V equals N R T. All right, and then our algebra is really simple to be able to solve for P. There's not even fractions that we have to worry about, right? In the combined gas law, there was things in the numerator and denominator, but now we've just got simple algebra, okay? So let's go ahead and solve for pressure. What unit will our pressure value be in? Atmospheres, yep. Okay, and I know that because I chose to use this R value, which means my pressure has to be in atmospheres. So I got a pressure value around 3 atmospheres, really, 3.02 atmospheres. Yeah, I see a red flag here because our initial quantity is given in grams, but what's the good news? You know how to convert grams to moles. It's so easy, right? You know how to do that already. So that's great, okay? We're going to convert this to moles before we start. We're also going to have to convert that to Kelvin, and we're going to have to convert that to atmospheres, right? I'm going to have to do a little bit of prep work here before I can even go into my equation for ideal gas law, okay? All right. Do you have it on your sheet? Or no?
No idea.
Okay.
Everything builds upon everything else.
Mm-hmm. This one says if a 20-liter tank contains that, what is the pressure in millimeters of mercury? So you're going to have to do a conversion at the very end. Very end, okay? Try this one on your own. Find the molar mass of a gas if 65.2 grams of the gas is stored in a 15.2-liter tank and exerts a pressure of 45 atm at a temperature of 60 degrees Celsius. So I'm going to give you a minute or two to get written down what you need to for this problem before we start working it together. So let's start looking at what we do have. We have volume. We have volume. We have pressure. We have temperature. And then we've got grams here of an unknown gas. So there's no way I can convert to moles because I don't even know what the gas is. So I'm going to hang on to that for a little while. And I'm going to go look at my ideal gas law and say, well, I can solve for the moles of this gas. I can solve for the moles present. So I'm going to go PV equals nRT. And I'm going to plug in my pressure, 45. I'm going to plug in my volume, 15.2. I'm going to solve for moles. And I'm going to plug in my temperature, which is not 60. It's 333. All right, and I'm going to solve for the number of moles that are present of this gas, right? I'm going to hang on to that grams it gave me for a little bit, but I'm going to solve for moles.
How did you do the algebra for that?
I just need to divide these over,
Oh, yeah.
okay? So multiply everything on the left, divide it by those two that are coming over. Uh-huh. We've got our number of moles, right? So now, remind me, what's the unit for molar mass?
Grams per mole.
Grams per mole. And so all I'm going to do here is I'm going to take my grams, 65.2, divided by my number of moles. And there's my unit, grams per mole, right? I'm shrinking down this ratio until it's grams per 1 mole. So 65.2 divided by 25 gives me a molar mass of 2.61 grams per mole. So probably not a gas here that I'm talking about, right? That's what I get when I make up problems. But we're nothing, okay? Because it can't even be hydrogen. H2, it would be 2, but
Called Nollium.
yeah, there you go. Okay, so it would be, I might ask you to identify a gas based on the molar mass, but we just need to know how to solve that, right? We're going to solve for moles, and then we take grams divided by moles. Sometimes we forget about the simple concept that is molar mass, right? It's how many grams per 1 mole of the substance. And so all we're doing is really reducing that ratio down to be grams per 1 mole, right? And that's it. But we get into this kind of, I don't know, systematic, like, operation of how we calculate molar mass, but really it's just grams per mole. So we can do that calculation together.